All right, so I tried to talk about structure preserving, machine learning, and data-driven structure discovery. I've tried to give this talk a couple times, but I never get to the second part due to usually time constraint. Hopefully, this time I can finish. Stan used to say, I don't really care about the time constraint. I talk all the content I want to talk about. The only thing that's going to change is my speed. But it's going to be hard for a mortal man like me, so we'll try. All right, so let's progress. So yeah, this is going to be two parts. The first part is a wonderful collaboration with Jeremy, who was a postdoc at UMass, and now he's an assistant professor at Texas State. And Ziyu Chen, who has shown up many times. He's a postdoc at UMass, and now assistant professor at UNC Chapel Hill. And Luke, who's my office neighbor at UMass, gave a talk on Wednesday. I don't know this guy, but he seems to show up in every talk. And the second part of the talk is also a sequence collaboration with Alejandro at SMU, Jimmy at ASU, who's also in the audience, and Panos at UMass, and also Hong Kong at UMass. Okay, so let's begin. So you've seen many diffusion model or generative model already, but today I'm going to talk more about GAN. So bear with me. I'll mention something about diffusion model as well, and probably in the end. So first, what are generative models? You've seen a lot of examples. Say you have a bunch of real images, and the generative model is to design some mechanism such that you can generate a bunch of fake images that look pretty much the same as real images. And mathematically, what does that mean? Well, we have a sequence of wonderful talks, but just to recap, you have a bunch of samples, x1 up to xm, coming from some distribution Q. That is an unknown target distribution. Probably some low-dimensional manifold. And what you want to do is that you want to learn a mechanism to generate new samples coming from some generated distribution PG. And you want this PG to be very close to Q. So the idea is how to do that. Well, how do we achieve this? I'll talk about how this is done in GAN. Again, this is kind of losing popularity, but it's still a very relevant and mathematically beautiful formulation. All right, so what are GAN? Intuitively speaking, GAN is a two-player game for learning a target distribution Q, which is accessible through a finite collection of samples. And the first player is called the generator, and the role of the generator is to, well, generate a distribution, and this is how it is done. You first specify some prior distribution. Say you have some Gaussian distribution, and you pick some random vector from this prior, and you feed it into this generator, it will spit out some sample. So essentially what it says is that the generated distribution is nothing but the push forward of the prior distribution, say Gaussian, under the generator, which is usually a neural network. And well, say if in the beginning you have some crappy generator, meaning that you're going to generate some crappy samples, and how do you make sure that this is very close to your unknown target? This is where the second player can come in. This is called the discriminator, and the role is trying to, well, make sure or tell the difference between those two. And how you do this is that you build some other neural network or some discriminator function, and you specify some discrepancy function with respect to the discriminator and the two distribution to tell the difference. Okay, so for example, one discrepancy can be chosen as the mean discrepancy. So you pick a gamma, which is the function, and you have two distribution Q and PG. The mean discrepancy is, well, take the expectation of gamma with respect to Q, subtracting the expectation of gamma with respect to the generated distribution. Say in the beginning, if these two distributions are very different, then it's very easy to pick a gamma that assigns, say, high values from Q, which are the real samples, and low values to P, which are the fake samples, so you can achieve a large discrepancy. So intuitively speaking, the role of the discriminator is trying to tell whether a sample is real and fake. And then once you have the discriminator and the discrepancy, then you can define some sort of variational representation of probability divergence, which Marcus and Luke talked about very extensively already. But here, usually it's defined as the maximum discrepancy as told by all discriminator gamma within your specified confunction class with respect to those two distributions. And one example is the Wasserstein-1 distance that popped up all the time. So this gamma is chosen to be the Lipschitz-1 function on the space X, and the discrepancy H here is indeed chosen as the mean discrepancy between two distributions. Okay, so now to sum it up, GAN is indeed nothing but a two-player game to learn a distribution. We want to minimize with respect to all generators, so this player here, such that the push-forward distribution or the generated distribution is very close to Q. And how Q is close to BG is measured by this maximum discrepancy as told by all discriminators within some function class that you have specified. Okay, so this is the setup. And well, the title of the talk is called Structure-Informed or Structure-Preserving Machine Learning. And indeed, in generative model, as Marcus has alluded to in his talk, indeed we have a lot of intrinsic structure in distribution. And one I will be focusing on throughout the talk is group symmetry. And here, say you have a bunch of medical images that are taken without orientation preference. Then the distribution Q you want to learn is invariant to a group, in this case rotation, meaning that an image and its rotated copy should have the same realness or same likelihood. So if you take a distribution Q and you rotate the image, rotate the sample, Q at the rotated sample is the same. So now, if you have Q under some group symmetry, how can you learn this distribution better? All right, so here is the setup. You have the same GAN framework, but now with an extra information that Q is invariant to some group sigma. Sigma can be any compact group or finite group, but that's usually what we deal with. So now the question is, how can you incorporate the structure, the group symmetry, into your GAN framework? All right, let's look at the first part of the generator. So the generator, as we understand, the role of the generator is to push forward the distribution or generate a distribution that mimics Q. And because we know Q, the ground truth target, has group symmetry, so the idea is that you want to generate an invariant distribution as well. And this can be done very easily. The simple idea is that you can specify some prior distribution that is invariant to a group. And then you build your generator to be equivariant to the group. Equivariant, I'll explain in a moment. Then automatically the generated distribution is invariant. So what does equivariant mean? It means if you have some group transformation on the input, equivariant network is built in such a way that it will automatically transform a, say, rotated input into some sort of a rotated output. Although those rotations can be different in different settings, but essentially you have two group actions on the input space and output space. If a rotation on input leads to a correspondingly rotated output, then you can show that, well, the generated distribution will be invariant to the group as well. So meaning that the symmetry information of the target distribution Q can be built into a smarter class of generator. All right, now let's turn our attention to the second layer, the discriminator, which is the more fun part. All right, so what is the role of the discriminator? The role of the discriminator is trying to tell, well, intuitively, whether a sample is real or fake. All right, so because now we know the target distribution Q and the generated distribution P are both invariant to the group, meaning that the realness or a fakeness of an image doesn't change after rotation. Meaning that to tell whether an image is real or fake, you only need to focus on the discriminator to be invariant functions. And indeed, to put it into a more rigorous framework, what it says is that if you have some pre-specified class gamma and you have some group action sigma acting on the sigma gamma, on the space X. And if the two distributions P and Q both are invariant distributions on the X, and then the maximum discrepancy as told by all discriminator within the original function class gamma, which is the original definition of the divergence, is the same as the maximum discrepancy as told by all discriminators within the smaller subclass of sigma invariant functions. So meaning that to compute the divergence, you only need to maximize over the smaller subset. And one of the issues in GAN training is usually the min-max optimization, where the interior supremum is hard to optimize. And we're saying that, as we'll show later on, if you have a better subclass of invariant functions, this will make the training much more stable and much more accurate. And we'll come back to the issue again, why this is important, because you're computing within a smaller subset. Right, and a fun story is that, well, I was actually given an internal seminar at UMass. I was talking about group invariant learning, and Marcus talked to me that, well, the next talk is going to be given by Jeremy on F-gamma divergence. And this is how it all started. It said, well, you need to pay attention to this gamma, and this is all the starting point of all a sequence of wonderful collaborations. Right, so let's just say, once you have all those symmetry or information into your players, what's the performance gain you can achieve? So this is to learn a rotated m-nist digits data set using only 1% of the training data, so only 600 images. On the left, you have ignorant players. Those are the players that don't know the underlying symmetry, and you're going to get some digits that don't look very well. It doesn't have high quality, and it's limited in sample diversity. And if you have smart players, you have much better sample quality, and it's also more diverse in the group orbit. All right, and you have the same picture, say, if you have medical images, a little bit more realistic. Then you have ignorant players. You have a lot of artifacts on the image, but this can be fixed if just some simple structure information into your players. Right, now let's get to this second part, well, the second part of the first part. What's the performance, what's the reason that explains the performance gain? So this will be separated into two parts as well. The first reason I want to focus on is what's the gain you can get from the discriminator subspace. So as we said, if you have two distributions that are both sigma invariant, then to tell the difference between two distributions, you only need to choose a smaller subset of sigma invariant discriminators. And what we claim is that reducing this gamma into its subset can provide a better empirical estimation of the probability divergence. So what do I mean by saying this? Let's just recall the divergence between two distributions is the, again, sorry to sound like a broken record, but it's like a maximum discrepancy as told by all discriminators within some specified function class gamma. Well, this is a well-defined quantity, but in GAN training or in whatever, to compute the divergence between two distributions, this is not really computable because you don't know the closed form formula for Q and P, and the supremum is hard to achieve. So what you typically do is that you take finite samples, which is like the real images in the field and the fake images that you generate, and then you replace this Q and P by their empirical measures supported on the finite samples. So you use this quantity to estimate the ground truth divergence. Right? So because of this smarter discriminator theorem, we say that, well, instead of taking the maximum with respect to this gamma, we can actually take the maximum with respect to the smaller subset of invariant functions. So now the question is, well, this is potentially a better estimator. So now the question is, how much better is this estimation? After taking into account group symmetry, how accurate is to use this, how much more accurate is to use this quantity to estimate the ground truth divergence? Right, the picture is actually much more nuanced. It depends on what type of group action you have. It also depends on what type of a divergence you have. And this is where Zhu came in. He did pretty much everything, did lion's share of the work. I just want to report a very simple example in which we analyze the sample complexity gain when we're looking at the maximum mean discrepancy, which according to Luc is the French that I really like. Anyway, so this is indeed the maximum mean discrepancy with respect to a class of discriminators that are unit ball in some RKHS with some specified kernel K. So this gamma is a unit ball in some RKHS where this kernel K defines the underlying RKHS. And our estimator to compute, to approximate the divergence is indeed something taking into account the symmetry of sigma. So you're looking at the empirical mean with respect to samples Qn and Pm, and you're taking the supremum with respect to this smaller subset. All right, so this is the result. Which says if you have some finite group sigma acting on the space X, and if you have two distributions that are both invariant to the group sigma, then your empirical estimation to the ground truth divergence can be computed using, well, has an upper bound that is bounded by the right-hand side. So here M and N are samples from Q and P. Of course, more samples, you're going to have smaller error, which is represented by this 1 over square root of M here. And you also have a constant capital A that you have a number capital A that depends on the group sigma and this kernel K. Again, K is the kernel which defines the MMD. If you choose different K, you choose different MMD. And sigma is the group. And you have a complicated formula for this capital A. It's related to some little a, and this sigma absolute value is the size of the group. And this little a is some number in between 0 and 1. It's complicated. I'm not going to write down the closed form formula. You can write it down. But I'll try to explain what it means for this formula. So let's first take a very simple assumption. Say if this little a is a number that doesn't change as sigma changes and it stays close to 0. If this is the case, then you can plug in this formula, then you're going to have 0 plus 1 minus 0 over sigma, so it's the square root of 1 over sigma. And now if you put into the right-hand side bound, you're going to have 1 over square root of sigma times m. All right, so this is a very intuitive result, which means to achieve the same level of accuracy on the right, instead of using m samples to achieve the same epsilon on the right, you only need m over sigma samples. So the idea is to achieve the same level of accuracy after taking into account the symmetry of the group, you only need, you have a reduction of sample complexity by the size of the group. Very intuitive, very naive. All right, now let's look at what would happen. As we recall, this A should be a number in between 0 and 1. Now, what if you go to the other end of the extreme? Say if A is close to 1. In this case, this capital A is going to be close to 1 as well. And if you plug in, wow, this is something that doesn't depend on sigma at all. So idea here, well, the explanation here is that, well, the implication here is that no matter what you do, to take into account the group, you don't have any gain. So it's only related to m, it's not related to the group. So meaning that you're doing a bunch of nonsense, or a bunch of things that make sense, but the rate doesn't make sense. So in reality, the situation is a little bit more nuanced. This sigma, as we said, is something that depends on, this A is something that depends on the group as well. So in the next example I will show, what happens is that A at the beginning, as sigma is increasing, at the beginning stay close to 0, meaning that as you increase the sigma, the rate will depend on sigma and will become better and better. And as you increase sigma to some point, suddenly this little a will jump to 1. And after that jump, no matter how hard you try, you will not achieve any additional gain because of this expression that doesn't depend on sigma anymore. Right. The example I was alluding to is the one where you have two distributions P and Q that are both invariant distribution 64 Gaussian mixtures that are invariant to different discrete rotation groups of size C1, C4, C16, C64, where CK is rotation by K angles, so C1 is just a trivial group, you're not rotating. C4 is the rotation by 4 angles, so 90-degree rotation, etc., etc. And we'll also be looking at MMD built with different kernels. So kernel are always chosen to be Gaussian kernel, but the thing is changing is the kernel bandwidth. As S is changing, you have a sharper decaying, faster decaying or slowly decaying kernel. And now the question is the estimation getting more and more accurate as you increase the size of the group? Going from C1 to C4 to 16, 64, is your estimation this guy, is it going to get better or worse? Well, how much better is it going to get? Right, so here's the result where the first case, you have a kernel that is slowly decaying. It's a kernel that has a larger bandwidth. So you can think of a kernel as slowly decaying. And the horizontal axis is the number of samples, so it's m and n. And the vertical axis is the left-hand side. You computed the divergence estimation. Here we know the ground truth should be 0 because you have two distributions that are the same. And as we can see, as m and n changes, the error becomes smaller. Different color shows the case when you have different group size. So sigma equal to 1 is the trivial group. This is C4, C16, C64. And you can see in this case, when the kernel bandwidth is large, you have a large difference between C1 and C4. But after C4, there is no additional gain as you increase the size of the group. So what happens is that in the beginning, this little a stays very close to 0. As you recall, if a is a little close to 0, then as you increase the size sigma, this thing is going to be getting smaller and smaller. And what happened later on is that as sigma gets close to 4, suddenly this little a will jump to 1. And once it jumps to 1, as you recall, nothing will change after you increase the group size. Right, so this is the case when you have a larger kernel bandwidth. And now if you decrease the kernel bandwidth, so it's still MMD, but the kernel is built from a Gaussian kernel with different bandwidth, then you can kind of squeeze more out of this MMD by increasing the group from sigma equal to 4 to 16. And what the picture happens here is that as you little a stay close to 0, and suddenly when sigma gets close to 16, then this will jump to 1. And to further decrease the kernel bandwidth, you can squeeze more out of this symmetry preservation. Right, so the idea that I want to convey here is that, well, you can put structure into your inference into your model. Intuitively, you're shrinking your hypothesis space, meaning that you will train a better model using less sample. But in reality, this is not always the case. Right, this picture will become even clearer, well, even more nuanced when you take into training into this entire consideration. So what do I mean by the training question mark? So let's try to explain this motivation in a hand-wavy way. So let's assume that you have a very large class of machine learning models. So this is all class of parameterized machine learning models. And we want to search for an optimal solution beta star. Let's say beta is some parameterized model, so it's not a parameter anymore. So beta star is the optimal solution of some learning task within this all class of machine learning models. And let's say the learning task has some underlying structure, in this case some symmetry, meaning that this optimal solution should belong to the smaller subset of symmetry preserving model. So ideally or intuitively should belong to a smaller subclass, should have the intrinsic structure. Right, to search for this beta star, you can proceed by doing two ways. You can either parameterize your solution using symmetry preserving model, meaning that you're actually, this initial model is preserving symmetry, and you parameterize all model to be in such a way that when you're doing gradient descent with respect to the parameter of this model, it will induce a trajectory in this subspace of symmetry preserving model, and let's say in a cartoon way it converges to some solution. Right, so this is kind of like a constrained optimization. You're optimizing within this small subclass, but it's optimization with respect to its parameter, which could be complicated. It's usually non-convex. On the other way, you can parameterize just as some generic standard model, so it doesn't have to respect the underlying structure. You take a gradient descent with its parameter and it will converge to some other solution. Well, even though this solution to which the generic model converge might not respect the underlying structure, in reality, it might be actually a better solution. Well, in the picture way, it shows that it's closer to the symmetry preserving model. And the reason why this could happen is because, well, once you change your model, change your architecture, what you actually change is the loss landscape. So when you're taking the optimization, you're not taking optimization with respect to beta itself. You're optimization with respect to the parameter of beta, which could be very complicated. So now the question is, can this kind of thing actually happen? So could it be that you're searching in the correct subspace, but you're making your search so much more difficult that it's hard to converge to the good solution? Right, so, well, will this happen? In the next example, which I will show, which is very closely tied to GAN training, the group invariant discriminate, well, if you have a group invariant binary classification, this will not happen. So it will always converge to a better solution. So you take into account the training process, it will also converge to a better solution. So here is the setting. You have a bunch of samples, xi, which are Euclidean input. So they are vectors in RD. And they belong to two different classes. So yi either belong to +1 or -1. So they belong to two classes. And we also assume that there is a group action on the space. So this is a group invariant binary classification task in the sense that the group action acting on the space will at any point living on the group orbit will have the same label. So in the picture I show, the group action is, say, the rotation around the z-axis, so SO2 around the z-axis. So the group orbit will be the circle. So any point living on the circle should have the same label. And well, now let's say we have your data that is like this. And to search for a classifier, you can either parameterize your classifier as a group invariant network, or you can parameterize your model as a fully connected network. But here we're assuming that there is no nonlinearity, but it's still a non-convex optimization because you have multiple layers. Okay, so you can parameterize your solution using either invariant model or generic model. And then let's say we train using gradient flow or gradient descent to convergence. So it converges to some limit. And now the question is the model that the invariant model converges to indeed better than a fully connected network? Right, so this is the result, which says the picture shown here is that, well, we have a high probability. So if you train your model to convergence, then with high probability, your generalization error, this is the generalization error because what it says is that once you train to convergence, you pick a new sample coming from your distribution, the probability of it assigning a wrong label is bounded by the right-hand side. So on the right-hand side, you have two terms. This is just the standard high probability term. You can ignore that. And this is the left-hand side term is something that relates to this quantity R bar. So what is R bar? R bar is defined as the distance of the group average the distribution to the origin. So what is the group average distribution? So meaning that you have a distribution in the beginning, and you look at all the samples in the distribution, and you take the group average. All right, so in this case, the group average, so if it's a SO2 around z-axis, group average, because the group orbit is going to be a SO2, it's a circle around the z-axis, so the average is going to be collapsing onto the z-axis. So meaning that the largest distance from your distribution of the group average is going to be R bar. All right, so this is what you get from training an invariant model. And now, what if you train a generic fully connected network? This is going to be something that is related to R, which is the largest distance of your original distribution to the origin. Okay, so now if your group action is a unitary action, then this operation of group average is always going to be an orthogonal projection, meaning that this R is always larger than R bar. So meaning that you will always have a better generalization result if you're taking into account group invariance in your parameterization of your discriminator. But the gain you can get is not necessarily, again, related to the size of the group. And let me try to explain what this is. Say now, if your group size is C1, the group is C1, so meaning that it's a trivial group, then this is just a fully connected network. Then your R bar is just the largest distance because group average is just itself, meaning that you're not averaging at all. So the distance is going to be R bar, which is this one, which is the fully connected result. And now if your group size is C2, so you have C2, then the group average is already collapsing onto the z-axis. So meaning that going from C1 to C2, you have a significant gain by the collapsing of the distribution onto z-axis. All right, now let's see what if you go from C2 to C4. Because the group average in this case doesn't change as you increase the size of the group, meaning that going from C2 to C4, you have no gain at all. Does that make sense? So what this shows again is that, well, you can try very hard to make your model to be invariant to even SO2 itself. But in this case, what I'm saying is that you don't need to do that. Going to C2 is already good enough. Going to any SO2 will only make your life worse. Okay, so this is the, yes?
So this depends on the data set?
Oh, definitely, yes. And also depends on your architecture.
Do these things give you an idea of like the dimensionality of your set or like manifold learning, I think?
Oh, very good question. So here the analysis I said in the beginning, it's even though it's like a cascade of different layers. So it's a cascade of linear layers. So even though the optimization is non-convex, in the end, what you parameterize is a linear model. So it's a linear classifier trying to classify distributions. So that's the reason why everything is collapsing onto a smaller, low-dimensional subset. Yes, it doesn't deal with manifold setting. That's what I want to say. Of course, you can make your, you can try to have a nonlinearity as long as it's a homogeneous nonlinearity. You also have implicit, I think Rachel has a lot of result on this. You have an implicit bias from the training algorithm. If you have a nonlinearity that is homogeneous, then you have a homogeneous network, but mostly in that case, implicit bias is established with respect to the parameter space, not in the function space. Yes, thank you for the question. Right, how many time do I have?
5, 7 minutes.
Okay, I'll try to just briefly touch upon the second point, second part, as I always do. So data-driven structure discovery. I'll talk about one work trying to discover conservation law, and the second part, I'll point to Jimmy, and he's a poster there, although he probably needs to move it away, so you probably need to go there fast. All right, so dynamical system and the conservation laws. Now let's look at, you have a 2D dimensional dynamical system. The xdt is equal to fx. So this is living in the state space within R2D. And what is a conservation law? Well, this is not the hyperbolic conservation law from Stan, so this is the conservation law in this dynamical system. Assume that you have a function I that remains constant over all system trajectory, then this function I over the state space is called a conservation law. And simple setting, if you have a harmonic oscillator, then the state space X is Q and P. And in this case, energy is conserved because in all trajectory, this quantity is conserved for any xt. Right, so, well, this is very nice. But the question is, now I just throw you a dynamical system. Maybe even worse, I just throw you a trajectory from this dynamical system. Without extensive prior knowledge of the system, how do you discover conservation laws from data? And even more ambitiously, how do you discover all of them? So what do I mean by saying all of them? I'll explain in a moment. Right, so we're focusing on 2D dimensional Hamiltonian system. For simplicity, we assume that this is in the canonical coordinates. So you have a symplectic matrix that is just a 1, -1, and you have a Hamiltonian H, and the vector field is parameterized at this. All right, so now let's given two functions that are defined on the state space, and we can define their Poisson bracket as, well, this is just the gradient of I times the symplectic matrix times the gradient of J on the right. All right, so this is the Poisson bracket, and now we have a bunch of conservation laws. What do I mean by saying all of them? There are two criteria. The first one is that we want the conservation laws to be functionally independent. Functionally independent meaning that you cannot have nonlinear combinations of those conservation laws that give you the trivial zero. So one cannot be expressed as the nonlinear combination of the remaining. And intuitively, by definition, it means the gradient of all the functions should be pointwise linearly independent in the state space. Well, it can be AE independent. And we also require the conservation laws to be Poisson commuting or in evolution, meaning that the pairwise Poisson bracket of the two conservation laws should be 0. Right, so some general fact, if you have a 2D dimensional, so D degree of freedom, if you have a 2D dimensional system, Hamiltonian system, that should be at most D independent conservation laws in involution. And if such conservation law exists, then this system is called integrable in the Liouville sense. Right, so now let's see, what's our idea of discovering all the conservation laws? It should be D in the integrable system, it should be less than D for non-integrable system. And the idea is inspired by the deflation method for computing steady states of PDE. Once you discover one, you fix the one, and then you try to find a method to deflate from that one such that you're only going to have to discover the remaining one. So learn conservation law one by one, ensuring function independence and in evolution. All right, so what's the algorithm of doing that? Well, when learning the first conservation law, this is very simple. You just want to learn some function that is indeed a conserved quantity. So you parameterize your function using whatever ansatz. Could be neural network, could be something that you like, a little library of some dictionary. And then you train it such that it is Poisson commuting with the Poisson bracket with self, and the Hamiltonian is equal to 0. So meaning that, well, this is like the gradient of the function and the gradient and the vector field should be orthogonal. So this means it's a conserved quantity. And the hat here denotes the normalized vector just to make sure you're not learning some trivial things. Right, once you have figured out the first one, how do you inductively learn this remaining one? The idea is, say, if I've learned the k-1 conservation law, and then you fix the previous one, and you're trying to search for the next one using this following laws. And what is this law? Let me try to explain. Well, on the top, you have conservation constraint. You want it to be a conserved quantity. And you have the involution constraint. These are very naive and very trivial. You want this to be a conservation law and in involution with the previous one. And the next one is more interesting. It's called the deflation part. And deflation is set up in such a way that at each point x, you want it to be living in a subspace that is not spanned by the previous one. And the idea is, if you are living in the subspace, then this is going to be creating a pool, meaning that this loss is going to be large. And essentially, once you have learned the one, then you fix the previous one, and then you search for the next one that cannot be living in the previous subspace. All right, you might say, well, this is an algorithm that kind of makes sense, but does it really make sense? We have a fake theorem that says it does make sense. When I say the fake theorem is that, well, assuming that you have all the conservation laws that are correct, learned to be perfect, And also assume that you have infinite samples coming from some, say, absolutely continuous distribution with respect to the state space, then this loss is equal to 0 if and only if the next function you learn is indeed the conservation law that is independent and in involution with the previous one. All right, you can make it less fake. This is something we have already done. That if assume that you have some perturbation that you have learned, say if I is close to the ground truth, then you can show that you can put a sample complexity bound instead of epsilon. You can say you have n samples coming from some distribution. Then with high probability for samples coming from those, this loss is less than epsilon, gives you a conservative quantity that is close to the ground truth conserved quantity that is in evolution with the previous one. All right, so let me just explain what this is used for in maybe 2 minutes. So if you have a harmonic oscillator that is in 2D harmonic oscillator, there should be 2 conservation laws because it's an integrable system. Indeed, this is what you show. When you're trying to learn the first one and the second one, the loss stays very close to 0. But when you're trying to learn the next one, you have a significant jump in the loss. And this alpha shows the deflation part of your loss. When alpha is chosen to be large, you're trying to push away from the previous ones. So you can see as you choose a larger alpha, it is pushing a lot away from the previous one. And you can indeed identify in the system there are 2 conservation laws, but when you're trying to learn the third one, it fails. And also performs very well on Hamiltonian lattice system. In this case, we are showing results for 4 Hamiltonian lattices. And for the total lattice, it's integrable, and this is FPOT is non-integrable. For discrete sign Gordon, it's non-integrable, and Calagero-Moser system is integrable. So you don't have to focus on this. Just take my word. Some are integral, some are integrable, some are not. Let's show the result for sign Gordon. Sign Gordon is sign Gordon and Calagero. Calagero is fully integrable, meaning that as you increase the lattice size, which is the degree of freedom, the number of conservation law detected should increase and will stop exactly at 6 or the number of sites. But if you have a sign Gordon, it's a system that is not integrable and it always has 1 conservation law, no matter how large the lattice site is. And indeed, this is what you see. When you try to learn the first one for the sign Gordon system, it's okay, but when trying to learn the second one, it significantly jumps. But for Calagero, it stays close to 0, close to very small epsilon, and only jumps at 7. So this is purely agnostic. You don't know anything. You only know the function. You don't know any property of the system. But you want to go to a higher degree of freedom. So now if n equal to 8, you have the same thing. For sign Gordon, it learned the first one, but the second one, it directly jumps. But for Calagero, it stays close to small epsilon, and it jumps exactly at 9. So it detects in the system there are 8 conservation laws. And you have similar story for Toda and FPOT. Toda, in this case, it's going to be fully integrable, so it stays close to small, and it will suddenly jump at 6, which is the degree of freedom plus 1. But for FPOT, it's non-integrable. It jumps directly. And it's a similar case. If you go to n equal to 6, it will jump at 7 for the Toda lattice. For FPOT, it jumps at 1. All right, there is one story in here that I didn't tell, which is a negative story. But if you know FPOT, there should be 2 conservation laws instead of 1. So our method only detects 1. The reason is because of the fake theorem only talks about one side of the story. So if the loss is 0, it means you have found a conservation law. But due to training and other instability, even if it's not 0, it doesn't mean you don't have a conservation law in the system. It could be, meaning that it's a good way to detect whether a system is integrable. But as a hypothesis testing, it's hard to say the other way around. To say the other way around, you really need to characterize how the training is done. Especially for neural network, this could be very difficult. Right? So I'm just trying to be honest here. Right? That's we can also do things if you are extending to trajectory. We can learn the Hamiltonian. We can learn the Poisson bracket, even though you don't know anything about the system. And we also have some results for learning lax pair, which is another way of detecting integrability. And Jimmy did the lion's share of the work, so I'll point you to him, who will happily explain all the results. All right, thank you all.